Hi, everyone. So in this portion of the video, we're going to talk about the composition of two linear transformations and how to find the matrix of that transformation relative to two bases. The nice thing is the composition becomes just matrix multiplication. It just takes a little while for us to get there, but using it's great, just great. So suppose you have finite dimensional vector spaces U, V, and W with bases B, C, and D respectively. Then if T is and S are linear transformations, T goes from U to V, S goes from V to W, we already know that S composed with T is also a linear transformation, and it goes from U to W. So then because of that, I should be able to find the matrix of the composition relative to B to D. And it winds up being that matrix is a product of two matrices. Each of them are just the matrix of a transformation. In this case, it's the product of the matrix of S from C to D with the matrix of T from B to C. Notice something really cool. It's a lot like matrix multiplication. It's very suggestive. You see how the inners are the same and the outer bases are what you have here, right? It's really kind of suggestive. It's really neat. Proving it's not difficult. It's a notational little nightmare though. So I'll show it to you, but we will use it a lot more than just showing the proof. So let VI be the ith vector in the basis for B. Because remember, to find out the ith column of the standard matrix for S composed with T, I have to apply S composed with T to the ith vector in B. So therefore, the ith column of this matrix would have to be the transformation applied to VI, but then I need its coordinates relative to D. All we gotta do now is just unravel that completely. So then we know that S composed with T of V is S of T of VI. So that's just the definition of the composition. But notice that we have S applied to something, don't care what it is, something, and I want the result relative to D. So by the theorem I gave you moments ago, to find that coordinate, you take the matrix of S relative to C to D, and you multiply it by, on the right, the coordinates of T of VI relative to C. Now I want to know, how do I find the coordinates of T of VI relative to C? Well, I can use the theorem again because it's T applied to something. So then to find out that vector, I take the standard matrix of T relative to B to C, and I multiply it by the vector VI relative to B. So then we have this equation, it's true. But the coordinates of VI relative to B, remember VI is one of the vectors in basis B. So that's just EI. Great. So why is that important? Because if you ever take a matrix, and this whole thing, this is just some matrix. If you take some matrix and multiply it by EI, that's the ith column of that matrix. So I just proved to you then that that's the ith column of the product of those two matrices. So since the ith columns of these two matrices are the same for every column, the matrices are equal to each other. And that's it. I'll just show you how to use it really quickly. So recall these two linear transformations. We had M went from P1 to P2. We had E went from P2 to R. I'm giving you the transformations all over again so you can see them. I'm giving the bases all over again so you can see them. And I'm giving their matrices relative to those bases. If I wanted to know what would be the matrix of E composed with M from B to D, I'd find the matrix of E relative to C to D and multiply it by the matrix of M relative to B to C. Notice how the C's are on the inside. When you multiply those together, you get the matrix 1, 3, 1, 1. That's it. That's what it would be. Now you might look at it and go, yeah, I don't believe you. Which don't blame you. Don't blame you. So why don't we just do it? I'm going to just take the image. I'm just going to take the image of some vector relative to this composition, and I'll show you what the answer should be, just like I did all the other times with the other examples. So the vector will be 2 plus 3x. That's a vector in P1. So then I take E composed with M of that. So it's E of M of V. So M of V, if you remember, all we do is take the polynomial, multiply by x. So that'd be 2x plus 3x squared. Then I take E of that, and E of that is I take the polynomial and I evaluate it 1, I evaluate it 2, and that would be then the vector. So the vector, this image relative to the transformation E composed with M, is the vector 5, 16. Great. So let's just do it again, just kind of do it in the other order. So we start with the vector. I'll find the coordinates of this relative to B, which is, since B is the standard basis, it's just 2, 3. And then I'll multiply that on the left by the matrix of E composed with M from B to D. So that's just the matrix 1, 3, 1, 1, the matrix I just computed for you, times 2, 3. And that's the vector 11, 5. Now you might look at it and go, but they're different. They're supposed to be the same. Remember, these are the coordinates of the vector. It's the coordinates of the vector. The vector is 5, 16. I gave the coordinates of that vector relative to D. So if we want to check it, if I write down the linear combination using basis D, using the coordinates, the entries in the coordinate vector 11, 5, I would get 11 times 0, 1 plus 5 times 1, 1. And that's indeed the vector 5, 16. Remember, the vector is 5, 16. Its representation relative to D is the coordinate vector 11, 5. And that's it. That's enough for that particular topic.